Hello dear students, in this subject groundwater assessment and we'll we'll continue about this well hydrology second chapter. And in the last class we are discussing about the steady flow in a confined aquifer. And in the topic we discussed that when the pumping starts from the well, there will be drawdown. Okay, the drawdown will start and the area of influence will gradually increase. Okay, that is the case of unsteady flow. But after a certain point of time, there will be equilibrium between inflow and outflow. Means I will become equal to Q. At equilibrium condition, the drawdown will stop and the area of influence will not increase further. So that is called steady state condition. After that, the steady state condition will prevail. And we derived this equation for steady flow in a confined aquifer, that is Thames equation. There is a discharge is equal to 2 pi kb into H2 minus H1 divided by ln R2 by R1. Where H2 and H1 are the piezometric head of two observation wells, and R2 by R1 is R2 and R1 is the radius of radius of influence of these two wells, observation wells. So this is the general equation that we developed in the last class, and also we discussed this equation of these themes if by putting different boundary conditions. Q is equal to 2 pi t into h minus hw divided by ln r by rw, where h is the piezometric head, maximum piezometric head, where drawdown is 0, means here, and hw is the piezometric head at well, Capital R is the maximum radius of influence, rw is the radius of well. This is the radius of well that we discussed. And here another equation we developed putting different boundary condition, 2 pi t equal to h1 minus h2 divided by ln r2 by r1. See, this is by observation wells. By putting this instead of this h2 minus h1, we can put this h1 minus h2. This h2 minus h1 means this difference. This difference is h2 minus h1. Instead of h2 minus h1, we can write h1 minus h2 divided by ln r2 by r1. And the last we developed this equation, that is, the discharge is equal to 2 pi t into hw divided by ln r by rw, where hw is the drawdown at well, drawdown at the well. This is the drawdown at well point, divided by ln r by rw. R is that is the radius of influence, and rw is the radius of well. So using these equations today we will solve some problems. The first problem here, it is given that the discharge from a fully penetrating well operating on steady state in a confined aquifer of 35 meter thickness is 2000 liter per meter. It should be liter per meter cube. It's actually meter per meter cube. Sorry. It is a discharge. So it is should be liter per minute. Liter per minute. It should be written like this: liter per minute. We can convert it into meter cube per second. Values of drawdown at two observation wells located at 12 meter and 120 meter away from the well are 3 meter and 0.3 meter respectively. Determine the permeability of the aquifer. So here R1 and R2 is given. R1 is 12, R2 is 120, and the drawdown S1 and S2 is given. To determine the permeability. So using this equation 3, this third equation we can use to solve this problem. S1, S2 is given, R1, R2 is given, and Q is given. So transmissibility can be determined and then permeability can be determined, because transmissibility is permeability into thickness, and thickness is given, that is 35 meter. Okay, so S1 is 3 meter, R1 is 12, S2 is 0.3, R2 is 120 meter, B is 35 meter, saturated thickness of confined aquifer. The discharge is, okay, this discharge just to convert in from milliliter per minute to meter cube per second. 1 liter is 1 by 1000 meter cube. Okay, 1 means 10 to the power minus 3 meter cube, and minute we have converted into 60 second, so it will be 0.0333 meter cube per second. So here, using this equation, we can calculate K. Okay, T is equal to KB, and B is given 35 meter. So you just put the values, you will get the answer. So K, it will be in meter per second. B equal to K into I. I is unitless, it's a Hadley gradient. So K unit is same as velocity unit. So this K is about conductivity, or you can simply say. So this is 1.29 into 10 to the minus per meter per second. Hydrolytic conductivity and permeability is same, unless it is written intrinsic permeability. Intrinsic permeability is different from this permeability or hydrolytic conductivity. The permeability aquifer is, we can calculate in meter per day. It is in meter per second. It is it's up to the okay, it's up to you. Can calculate. It's not given that it will should be in calculating. So in next example, the discharge from a fully penetrating well under steady state condition of confined aquifer of 30 meter thickness is 2100 liter per minute. The drawdowns observed at two observation wells located at 50 meter and 150 meter from the well are 3.2 meter and 0.2 meter respectively. This is similar to this example, is similar to this example 1. Determine the transmissibility and the permeability of the aquifer. The same thing. Well, the data is different. Means here B is 30, and Q is 2100, 2100 liter per minute. Drawdowns S1 and S2 is given. S1 3.2, S2 is 0.28, R1 is given 15 meter, and R2 is 150 meter. So this data is given. Okay, B is given 30 meter saturated thickness of confined aquifer. The discharge is given 2100 liter per minute. 1 liter is 10 to the power minus 3 meter cube. I mean, it is 60 seconds. So you can convert it into meter cube per second. Next, in this equation, third equation you can put, and you will get the transmissibility. Okay, and also this permeability can be calculated. You can mark here transmissibility unit is meter square per day. Okay, so it will be meter square because K T is equal to K into B, so it will be meter square per day. Next example, a 30 cm dia well completely penetrates a confined aquifer of permeability 45 meter per day. The length of the strainer is 20 meter. Length of the strainer means this width, this thickness. The B is given 20 meter. On steady state of pumping, the drawdown at well was found to be 3 meter. Means RW is given. Drawdown is given. So SW is given. This SW is given, and the radius of influence was 300 meter. Means R is given. Calculate the discharge. Q we have to calculate. So SW is given, R is given, B is given. So which equation we should put? So here this equation is suitable. Okay. Radius of well is also given. R is 300, SW is 3 meter, B is 20. Diameter of the well is 30 cm diameter. Diameter is given, so radius will be 30 by 2, 15 cm or 0.15 meter. So K is given. A steady state drawdown is given, radius of influence, calculate that discharge. Okay, permeability is given 45 meter per day. 45 meter per day. we can convert it into meter per second. So T will be K into B, okay, and then the discharge you can calculate. Okay, it's very simple. So next example, for the well in the previous example, calculate the discharge if the well diameter is 45 and all the data remains same as in example 3. If the drawdown is increased to 4.5 meter and all other data remain unchanged in example 3. So in this 2 bit, you can solve it. It's very easy. Only we have to observe that if well diameter is here it is 30, well diameter is here 30, here it is 45. If by increasing well diameter, how it affects the discharge. So here the diameter is given 45. So RW will be here 45 by 2 be 0.225 meter. So the discharge you can calculate. Okay, all the data remains same. So it will be 0.0272 meter cube per second. So by increasing the diameter, there is 50% increase in the weight. Okay, there will be increase of discharge by about 5.4%. By about 5.4% increase in discharge by increasing 50% in well diameter. Okay, so here in the second bit, SW is given here. The second bit, if the drawdown is increased, means so drawdown to well, SW is increased to 4.5 meter. Okay, 4.5 meter, and all other data is remains constant. So you can calculate the discharge. It is 0.0387 meter cube per second. So another the discharge, since the discharge here Q is directly proportional to SW, so it is there will be linear relationship between these two. So there will be linear variation will be there with the drawdown. Okay, when other factors remain constant. So these things you should observe. Okay, so this much. So next question is I'm giving you as a assignment. Okay, this is the first assignment. An aquifer pump test was conducted in the confined aquifer. The thickness of the aquifer is 25 meter. The well was pumped at 31.54 milliliter per second. After 1 day, the drawdown observed at 2 observation wells located at 50 meter or 100 meter from the pumping well were measured at 0.8 and 0.37 respectively. As steady state condition, estimate the transmissibility and permeability of the aquifer. So here you see the thickness is given, B is given, the well is pumped at this discharge is given, the drawdown observed in 2 wells located R1, R2 is given, and S1, S2 is given. So equation 3 you can use to calculate the transmissibility and permeability. Okay, discharge is given. If the diameter of the well is given and the piezometric head at 2 observation wells are located, means R1, R2 is given from the pumping well were measured as this. Means here piezometric head H1 and S2 is given, R1, R2 is given, a diameter of RW is given, calculate the magnitude of piezometric head at the pumping well, means HW. It is asking HW. So for this, you have to use which equation? This here, this equation first can be used. Here, piezometric head at the 2 observation well is given. So first equation 1 can be used, okay, and then it can be used to calculate this K, okay. Then after that, then it is asking HW. Then another equation we have to use to calculate the HW. Okay. So here this is the assignment, and you have to solve. You have to put your mind to calculate this second bit. Okay. So thank you so much.